Welcome to the Explainer. Every single day, the sun blasts our planet with a colossal amount of energy. But have you ever stopped to think about where it all actually goes? Well, it turns out that journey has three main paths: reflection, scattering, and absorption. So today, let's follow the light and see how these paths create, well, everything from our weather to the very color of our sky.
So, let's dive right in with the big question. When that sunlight, after traveling 93 million miles, finally gets here, where does it all go? You know, the answer to this one question pretty much governs our planet's climate, it powers all life, and it even paints our sky blue. It's a bigger deal than you might think.
Okay, here's the breakdown right up front. Out of all the solar energy that reaches us, a pretty surprising 30% is just immediately reflected right back into space. Gone. The atmosphere and the clouds, they soak up another 20%, and that leaves just half, only 50%, to actually warm up the land and our oceans. So let's start with the energy that basically gets turned away at the door.
That 30% of energy that bounces right back into space? Well, it's all governed by a single, really crucial concept: albedo. You can think of it as a measure of how well our planet acts like a giant mirror.
So what is albedo anyway? It's actually pretty simple. Just think of it as a reflectivity score. A surface with a high albedo, like fresh snow, reflects a ton of light, and one with a low albedo, like, say, dark asphalt, just soaks it right up.
And just look at the huge range of albedo you see in everyday surfaces. Fresh snow, it can reflect up to 90% of sunlight. That's exactly why it's so blindingly bright on a sunny day. Now, compare that to a dark forest or an asphalt road. They absorb almost all the light that hits them. And this simple difference, it has massive implications for local temperatures.
This is where you can really, truly see the power of our atmosphere. Earth's total albedo is about 30%, and that's mostly thanks to our bright reflective clouds. The moon, on the other hand, its albedo is just 7%. We think of it as this bright object in the night sky, but it's actually a very, very dark rock. If you were standing on the moon, Earth would look like a brilliant, dazzling blue jewel in a totally black sky.
But not all the light that heads back to space is cleanly reflected like that. Some of it gets scattered, which is a much more chaotic process that just so happens to be responsible for the very color of our sky.
So here's the key difference. Reflection is orderly, right? Think of light hitting a mirror. It bounces off at a predictable angle. Scattering is pure chaos. It's like light hitting a disco ball. It smacks into tiny particles in the air and gets sent flying in every possible direction.
And this scattering is actually incredibly useful for us. It creates what we call diffused light. It's the reason you can read a book in the shade of a tree instead of sitting in pitch black darkness. The atmosphere scatters light everywhere, filling in the shadows. On the moon, though, where there's no atmosphere to scatter light, shadows are stark and absolutely totally black.
Okay, so this brings us to one of the most fundamental, classic questions out there. If the atmosphere scatters light, why does it scatter blue light specifically? Why isn't our sky green or violet or maybe just plain white?
It all comes down to size. The tiny little gas molecules in our atmosphere, they are the absolute perfect size to grab onto short wavelengths of light, like blue and violet, and just scatter them everywhere. They're just not the right size to do the same thing to longer wavelengths like red and orange. So all day long, that blue light is just getting ping-ponged all over the sky, reaching our eyes from every direction and painting our world blue. So what about sunsets then? Well, when the sun is down on the horizon, its light has to travel through a much, much thicker slice of atmosphere to get to you. And along that long journey, pretty much all the blue light gets scattered away from your line of sight. So what's left to make it all the way to your eyes? Only those long wavelength reds and oranges, creating those spectacular colors we all love.
All right, so we've covered the 30% of energy that's lost to space. Now, let's finally look at the remaining 70%, the energy that is actually absorbed by our planet and warms it up. So before sunlight even has a chance to reach the ground, about 20% of it gets absorbed directly by clouds and gases floating around in the atmosphere. This warms the atmosphere from within. The last 50% makes it all the way down to the surface.
The key concept here is that the atmosphere is a selective absorber. What that means is that different gases are kind of picky. They only absorb specific wavelengths of energy. But one of the most surprising selective absorbers on the entire planet isn't a gas at all. It's snow.
This is so cool because it reveals a fascinating paradox.
We just established that snow is one of the most reflective things on Earth, right? But here's the twist. It's also an excellent absorber of infrared radiation, which is just heat. So while it reflects sunlight coming down, it absorbs heat radiating up from the ground. It actually acts like an insulating blanket, which is why farmers often hope for a good snow cover to protect their winter crops.
Okay, we've covered a lot of ground. Reflection, scattering, absorption. So let's bring it all together with a quick visual summary. A little mind map of sunlight's complete journey.
So let's recap sunlight's 3 fates, shall we? 30% is lost to space. That's a combination of reflection and scattering that determines our planet's brightness and gives us our blue skies. The other 70% is absorbed, split between the atmosphere and the surface, and that provides all the heat that drives our climate and, makes life possible.
At the end of the day, the big takeaway is that this energy budget, this incredibly delicate balance between what's reflected and what's absorbed, is what makes our planet habitable. And that leaves us with a final and pretty crucial question to think about. If we were to change our planet's albedo, even by just a tiny amount, what kind of chain reaction would we set in motion?